Oh, I forgot to get a coffee. Brilliant. Hello, everybody again. So welcome back to the second talk of the morning session. And we're glad to have Vishnu Jala from the University of Witwatersrand talking to us about probing the EBH limit of supersymmetric ADS black holes. Over to you, Vishnu.
Thank you. Well, welcome to my kitchen. Thanks to the organizers for arranging this wonderful conference. I missed some of the talks because of the teaching, but the ones I've been to have been great and educational and enlightening. Well, thanks for the invitation to speak. I look forward to being in Lisbon at some point to see all of you in the next iteration, maybe. So I'd like to tell you a little bit about some work I've been doing regarding using recent developments with the superconformal index to examine a certain class of black holes, extremely vanishing horizon black holes in ADS. So there we go. So some brief motivation. We know that if we have black holes in ADS, say ADS5, extremal black holes will have a near horizon ADS2 region. And sometimes this is enhanced to higher dimensional ADSs in the near horizon. So we know that we can compute the black hole entropy either from examining the asymptotic CFT or from examining the near horizon CFT. And we'd like to get some understanding of how to develop the counting on both sides and see how the states on one boundary CFT map to states in the other boundary CFT. The recent developments with superconformal index allows some progress on this, although I think we're rather far from a complete solution to understanding how states map explicitly. So we know as well that there are lots of black holes for which this kind of structure is evident, and they needn't even be extremal. So for example, if you consider the 2R-charged black hole in ADS5, the near horizon has an ADS3 factor. And if we focus on the near horizon, we get the BTZ. The BTZ is described in terms of angular variables based on the focusing. If you integrate over the angular variables, you recover the entropy of the 2-charged black hole. For these R-charged black holes, these superstars in ADS5, there is some naive state counting you can do in CFT4 by just examining the operators that preserve a certain amount of supersymmetry and then introducing defects in all possible ways. Vijay talked about something similar in his talk, if you'll recall. This naive state counting in terms of extremal operators plus defects also recovers the entropy. So at least in the CFT4 side, we have some understanding of the microscopic origin of the entropy of this class of black holes. And of course, in ADS3 CFT2, we also have some microscopic understanding. And it will be very good to realize how states on one side map to the other. We also know that certain degrees of freedom in the UV and the IR CFTs can be connected. And based on some work I did with Suresh and collaborators, we've noticed that if you consider C functions associated to the ultraviolet CFT and the infrared CFTs, there's a monotonically decreasing flow that arises via the attractor mechanism. The scalar fields phi I and the bulk, these are dual operators sourced by coupling constants in the boundary, and the C function is extremized at the endpoints, so phi I prime equals 0 there, and we can construct these C functions that connect the ultraviolet CFT and the infrared CFT, and these needn't even be in the same dimension. The C function, however, is of course not unique, and its non-uniqueness may be related to scheme independence and bulk diffeomorphism invariance. The story is suggestive of our ability to make connections between these different CFTs, and we'd like to explore these connections a bit further. In this story, essentially, what we have is the attractor mechanism provides us a gradient flow, And if you combine this with a null energy condition, you can think about the C function as being given to you by the superpotential, basically, in this n equals 2 supergravity theory. And this is a non-vacuum to non-vacuum flow. So this is sort of an aside, but some motivation for how to connect aspects of these different CFTs to each other. So the basic question then is, how do degrees of freedom in the UV connect to degrees of freedom in the IR? And if there's a microstate picture, can we follow an ensemble of states describing the black hole entropy on one side to the other by following an RG trajectory? Here, extremal black holes have an ADS2 and ADS3 near horizon. So we'd like to understand how the CFT1 or CFT2 that we see in the near horizon region is realized from the CFT4. And this is a rather unusual realization because the CFT4 has a finite number of generators, whereas the CFT2 has an infinite number of generators given to you by the Virasoro algebra. We'd like to expand on this a bit further, and then ultimately we hope to generalize this to the non-extremal setting where we see semi-realistic black holes in ADS. Okay, so with that motivation, let me briefly mention the outline of the talk. First, I'll discuss extremal vanishing horizon black holes, and then I'll review the index counting. This is an area in which there are many experts in the audience, and so I'll hopefully, well, I'll be brief and hopefully not say anything wrong. Then we'll discuss the origin of the IR CFT from the UV CFT, and then I'll discuss the prospectus for future work in this direction and unresolved problems that we've encountered. So let me begin by just stating the punchlines, the main results. Techniques for analyzing 1/16 BPS black holes that have been developed apply to the EVH CFT2 correspondence. The entropy calculation for the EVH and near EVH black holes we study occur in the fast rotating limit. We find the Legendre transform of the superconformal index, which gives a black hole entropy, is equivalent to a derivation of the CARDY formula. And we'll see how aspects of the IR CFT are realized in UV CFT, and there are hints of similar stories that exist in higher dimensions. Okay. So, right. Why am I not advancing? There we go. So this is work I've done in concert with a number of collaborators. Kevin Goldstein, who's at WITS, Yang Lei, who's a postdoc shared between WITS and the Niels Bohr Institute, Sam Van Leben, who's a postdoc at WITS, and Wei Li, who's the Chinese Academy of Sciences. In particular, I should say that working with the postdocs, Yang and Sam, has been very educational. I've learned a lot in this process. Most of the talk is based on the paper 1910-14-293, but there's forthcoming work along this theme as well. 2009 may be a bit optimistic, but let's say before 2010. All right. So this slide may be a bit unnecessary and overkill for this audience, but it's certainly worth noting why string theory is the right language for addressing these problems. We know the Schwarzschild radius scales with a Newton coupling, and this tells us the size of the black hole increases as you make gravity stronger. Most gravitating systems, however, become smaller as the interaction strength increases, and the fact that string black holes get larger with gravitational coupling is indicative that this is the right language for addressing these sorts of issues. So we're heartened by this result, and we aim to exploit these ideas using our string technology. So we're studying extremal black holes. These extremal black holes are in ADS, so we'll have ADS-D plus 2 asymptotics. And then in the near horizon region, there'll be an ADS-2 factor times some other auxiliary space. The near horizon ADS-2 is often enhanced to a higher dimensional ADS, for example, ADS-3. Near the throat, close to the horizon, we'll have a near ADS-2 region. We'd like to endow this ADS-2 with some dynamics that we can play with and exploit. So how does one go about doing that? Well, we can deviate from pure ADS2, and this idea has some recent resonance in terms of the SYK model, random matrices, etc. This is also stuff that Vijay talked about on Monday. We can make the UV-CFT defined on a non-compact space. This gives us a continuous spectrum with non-trivial dynamics at low energies. This is sort of the philosophy adopted in ADS condensed matter. Or we can also employ what's called the extremal vanishing horizon limit. In this limit, we decrease the mass gap by setting the central charge to be large, and then we notice the states are separated by 1 over the central charge. The entropy will scale like the central charge times the area of the black hole, and to keep this quantity finite, we'll send the area to 0. So this is the basic idea that we'll adopt in performing this extremal vanishing horizon limit of these black holes. Okay, so if we take a low temperature expansion of the entropy, there's be a factor which is just given by the charges, and then corrections with powers of temperature. If a leading correction of the entropy scales like t to the k, then there's a CFT k plus 1 in the infrared, which points to ADS k plus 2 near horizon regime. In particular, for k equals 1, we have this ADS3 factor. In the limit where the entropy goes to 0 and the temperature goes to 0, we keep the ratio of entropy and temperature finite. The effective CFT2 we obtain in this corresponding to this ADS3 allows us to study dynamics for this EVH black hole. And there are EVH limits of this type for ADS4 and ADS5 black holes that we'll look at. So these ideas were really developed by Sheikh Jabari and collaborators based on some superstar work that Vijay, Shawan, and I did maybe more than a decade ago now.
Sorry, Vishnu, is there some simple prototype for this, maybe based on these examples? Can you, so that we have this in mind? What kind of CFT do you get at the end?
The CFT is just symmetric product type CFT. I mean, it's sort of analogous to D1, D5.
But what happens to these limits? I thought there's something you do to the CFT. Or not?
I'm not sure I understand the question. What were you asking?
So what is the statement that it's the usual D1, D5 type CFT? And it's in like gravity, that's dual to something funny in gravity that you have to do. Is that the point?
The prototype example is really a 2-charge superstar. In the 2-charge superstar, if you take the near horizon limit there, even in the non-extremal case, there's an ADS3 factor. That ADS3 factor is effectively describing some BTZ-like black hole. By looking at the entropies of these BTZs, you recover the entropy of the black hole from the the ADS5 cos size 5 perspective as well.
So just to clarify, so this will not, does this work for supersymmetric black holes where S0 of Q is already large, will never go to 0?
Morally, there's no obstruction to this happening. I believe that the 1/16 BPS solutions that you studied, for example, there's no EVH limit there per se of this type. But
yeah, that's exactly what I was imagining, because S0 of Q is non-zero and large. You can't.
Right. But if you look at these non-extremal solutions, and there is a BPS limit where there's a vanishing horizon, right?
Yes.
That's the sort of setting that we're looking at.
Okay, thank you. Thank
you. Other questions? You good? Okay, so if we look at some static ADS5 black hole, we have the metric with certain scalar harmonic functions, and the S5 we think of as a T3 vibration with S2. These black holes, have various charges we can compute by Komar integrals, and we're going to look, instead of the static case, we'll look at the rotating case, and we will use certain parameters like mu to describe the deviation from extremality. There's a critical value, mu critical, below which there's a time-like singularity. So we'll work above this critical value. We'll take particular scaling limits of our solutions. So we have some understanding of the 4D description of these rotating black holes, whereas with static supersymmetric black holes in the extremal limit, the BPS limit, there are singularities in these geometries. So we'll include rotation, and they're generically 2 angular momenta and 3 R charges. And these solutions were developed initially by Gutowski and Rial, but subsequently expanded upon by various groups. Beyond ADS5, there's similar stories in ADS4, ADS6, and ADS7. And I'll mention these later in the talk. So the metric is complicated. This particular metric was written by Chong, Spedish, Liu, and Pope. Rather than going through these calculations in detail, I'll be somewhat impressionistic, and we can write down, we'll show the work in the paper, of course, but here, for the purpose of the talk, I'll be a bit more sketchy. So these non-BPS black holes have 4 parameters, which we call A, B, M, and Q. The BPS solution will have 5 parameters plus a constraint. So the supersymmetry condition here is that the energy is the sum of the angular momenta plus the sum of the charges in the appropriate units. We get a singularity-free geometry when the horizon size is fixed, and the chemical potentials corresponding to this are generically complex. So we can write down the partition function using methods that are developed by people in the audience. And in the 0 temperature limit, as beta goes to infinity, the partition function localizes on the states to satisfy a BPS equation. Roughly speaking, energy equals angular momentum. However, for the partition function to be well defined, one should scale these quantities appropriately, and we have delta and omega is equal to b times 1 minus phi and b minus 1 minus omega respectively. So this then defines a BPS limit of these chemical potentials, and we have some constraint equation that relates these deltas, these omegas, to some complex number. In the EVH limit, we start off with non-extremal solution, and then we work at criticality, where mu equals mu c equals q2 times q3, and we get the some metric which describes ADS3 and some compact space. So the construction due to Shakespearean collaborators is effectively like a generalized BMM limit, in which we see that the quantities scale with powers of n, and there's an epsilon parameter which essentially describes deviations, which describes the near horizon limit that we're taking. All right, so this is the near horizon limit in particular. In this limit, the entropy vanishes if the quantities A and B scale with epsilon, and there's a singularity-free solution when these exponents are related. So we can choose S scales like T, scales like epsilon. The BPS EVH condition sets B equal to 0. And in this limit, we find an ADS3, which decouples from this in the 7-dimensional auxiliary space. So this gives us the extremal vanishing horizon limit of a particular class of these black holes.
Sorry, may I ask something?
Yes.
So is there a non-trivial intersection between this limit and the BPS limit?
The EVH limit and the BPS limit. Yeah, I mean, there are EVH black holes that are BPS.
So what I mean by the BPS limit is the same limit that you showed before.
Yes.
So there is an intersection then. That's
Yes.
it.
Yeah.
Okay. Thanks.
So, right. Instead of setting B equal to 0, if we leave B scaling like epsilon, we have a near EVH limit. In this limit, the effect is to replace the ADS3 in the infrared with BTZ. Here, the central charge will scale with epsilon, and the entropy will also scale with epsilon. In effect, we've got a double scaling limit where n goes to infinity, epsilon goes to 0, and some quantity epsilon n squared is being held fixed. So this is the near EVH limit. These black holes will have a small horizon.
But then, I mean, let me ask something. So you said that the entropy in this limit vanishes. Hmm?
The entropy in the EVH limit vanishes. The near EVH limit, there is an entropy that's epsilon.
I see. Okay, thanks. Very good. Okay, no, I'm still. In the pure. Okay, so what you're saying is that
the EVH limit, the area is 0. So the Bekenstein-Hawking entropy is also 0.
Sure. But what you're saying is that then you are taking on a scaling. You are not really at the point. Well, it's the same as the. So you're also taking on a scaling of the quantity.
Yeah.
Okay.
We're in the near EVH limit. We have the entropy scaling like epsilon n squared times some prefactors. Now this can be macroscopic if epsilon n squared is large. Epsilon n squared is small compared to n squared, but epsilon n squared can be a large parameter in itself. This is sort of what happens with the defect story I mentioned earlier with the superstars. If you think about a sensible solution in supergravity there, the condition for that to happen is that the number of defects you introduce is parametrically scaling with n squared. But still, the prefactor epsilon could be like 10 to the minus 6 or whatever. It means n squared is going to infinity. So as long as epsilon n squared is reasonably large, we still have a well-described supergravity limit. The same story here. We have epsilon n squared can be a large parameter. It's just much smaller than n squared.
Okay, let me just to be sure that I understand. So there are a series, I mean, one can classify all the possible limits that you can take to this BPS solution.
Yes.
Your EVH limit is one of these.
This is a limit, yes.
It's one specific, okay. Thanks.
Vishnu, I had another question. So in this lambda on the first line goes to infinity then in this limit? Is that right? Lambda is like n squared, roughly speaking.
Lambda is an order 1 number here, I think. I mean, we want epsilon going to 0, n going to infinity.
So I see. So B actually goes to 0.
Yeah.
B goes to 0, I see. And another question is in the second line, there is this word decoupled. So what is the asymptotics? It's ADS3. So you're saying instead of pure ADS3, you get ADS3 asymptotics with the black hole inside it. Is that the point? Yeah,
the near EVH limit, instead of pure ADS3, you've got BTZ basically.
I see. So somehow the fact that B is not 0 doesn't propagate to the ultraviolet of the ADS3.
Yes.
I see. That's interesting. Thanks.
Okay. So yeah, this is a setting. So in assessing various saddle point calculations later, we'll take n squared epsilon, or alternatively 1 minus a to be small. So either n squared epsilon is large, 1 minus a to be small in order to justify various saddle point calculations later on. So these are large parameters in a certain sense. All right. So in the EVH limit, Bercuse and collaborators have suggested some dual operators. I'll return to this point later in the talk. In the near EVH limit, we'll have these complex values for fugacities, and we'll have some chiral Virasoro generator, which will scale like this combination JB plus Q3, and we'll see how this arises in the CFT4 later on in the talk. All right, so regarding the BTZ, if we take the if we take the extremal vanishing horizon limit of the BTZ, we're scaling certain parameters in this geometry. Effectively, when we do the scaling, we get another BTZ, except there's now some deficit angle associated to that. The entropy will scale like this parameter epsilon, and we effectively have a pinching orbifold of the kind that Jan de Boer looked at. So to have finite dynamics, we should also scale the central charge, and the conformal field theory in the infrared in this BTZ story looks like some symmetric product of CFT in the ultraviolet with this factor 1 over epsilon. The central charge in the UV goes to infinity, but the central charge that's physical in the IR is this product epsilon times n, which we hold fixed. And then we obtain some Virasoro generators based on the original Virasoro generators in the parent theory. So that's sort of the picture that we've got for the CFT description of this geometry. So the superconformal index enables certain computations in this respect. So we start with a partition function, n equals 4 super Yang-Mills, restricted to a hypersurface which satisfies certain relations among the chemical potentials. And this partition function in particular will localize to 1/16 BPS states due to the beautiful work of Alejandro and Samir in the audience and their collaborators. The result we obtain is this n equals 1 superconformal index. So n equals 4 super Yang-Mills, we have, as we all know, 6 scalars, 4 evolved fermions, and a vector gauge field. Plus there'll be descendants that act, that arise from acting covariant derivatives. We can write down the single particle partition function, the BPS limit. And the story effectively restricts the SU1,2/3 subsector of 1/16 BPS states. We can examine how to realize such states. And in global coordinates, in the dual global coordinates, we describe certain fields as giving rise to these states. So in the EVH story, in the strictly EVH story, we have a vanishing horizons. We're really looking at the 1/8 BPS states, the SU1,1/2 subsector of this the story. The blue states correspond to the fermionic subsector here, and the red and the blue correspond to the 1/8 BPS sector. Right, so now we can use the plethistic program to write down the partition functions. So if we consider some function, f of x equals described by some series expansion, the plethistic exponential is derived from this function. So this was developed in our areas by Bofeng, Amihanani, Yang He. It's a wonderful tool for counting gauge invariant operators. And as an example, one can look at, for example, SQCD. And the Hilbert series you obtain from plethistic exponential essentially tells you the kind of states, kind of gauge invariant operators you have in your theory. In this theory, for example, we have NF squared mesons of weight 2, 2 baryons, each of weight NF, with some constraint which relates the mesons to the baryons. So this is a powerful tool for considering gauge invariant operators in various theories. In the context of black holes, this is effectively studied by Haroni, Barsana, Minwala, Papadopoulos, and Van Rijnsdonk when they promoted the single particle partition function, which they described as the sum of oscillators, to the multi-trace partition function. So applying these methods to the single particle partition function that we previously obtained, we can write a multi-letter partition function in the story. And this partition function is described by various parameters associated with the weights and the roots of SUN. And this construction is valid in the free field limit. Okay, so to review this story, we consider large n limit of log z, and the initial feeling was the free flow result could not capture the black hole entropy, but this perceived wisdom was recently reevaluated. So initially, Zaffaroni and collaborators showed that the supersymmetric black hole entropy of the Legendre transform of a quantity which can be interpreted as a supersymmetric Casimir energy. And then in this beautiful work, which inspired many later developments, it was shown the partition function and superconformal index are related to the supersymmetric Casimir energy. And then using matrix model intervals and beta Ansatz techniques, the superconformal index is shown to have a leading n squared term. So there have been various developments on this, some of which we heard about from Samir on Monday. So I'd like to illustrate the spirit of the calculation without getting bogged into the details. So this is a zeitgeist, if you will. The idea is we work in some CARDY limit where there's a hierarchical scaling of parameters, and then we compute using this limit, the partition function. So based on applying usual math tricks and saddle point method and so on, we can determine the entropy. So the various assumptions that go into this. One assumption in particular is the dominance of certain saddles over other saddles. So we find that the entropy will scale. Yes.
This thing, this free field computation that you wrote down one slide ago, is that the index, or is this like, is it trace -1 to the f or trace 1?
Sorry, what? I didn't hear you.
Are you considering the index or the partition function? Is it trace -1 to the f or trace of 1?
It's a partition function, I believe.
So this is not, for instance, this is different from what I was discussing, right?
This is what the Korean group discussed, I believe.
That's the same. I don't know which paper, but let me. Looking at this expression, it looks like the index.
Let me see.
It is the index. It is the superconformal.
It is the superconformal index. Then I'm a little confused about something. The superconformal index is supposed to describe the supersymmetric, should be dual to the supersymmetric black hole. But according to our earlier discussion, like 10 minutes ago, I thought the black holes you are describing are not supersymmetric.
The EDH BPS black hole is supersymmetric. It's 1/8 BPS. You can go away from supersymmetry and extremality for that. That's a near EVH case.
So sorry, but it's 1/8 BPS. So that's certainly not this index.
So the EVH black hole we were looking at had 0 horizon, right? So it was it's not the 1/16 BPS black hole you were looking at, no.
Okay, good. So then why is this index relevant?
The 1/8 BPS is a special case of your case, right?
I think, sorry, if I can chip in. So the near EVH black holes that have a finite entropy, they're still BPS, and those guys are 1/16 BPS, and they should be encoded in this specific index.
Exactly. So that's what you said, the vision, no? That there is an intersection, no?
But I'm totally confused. The 116th BPS black holes have entropy of order n square. These ones, according to what Vishnu said a couple of slides ago, don't have n square entropy. It has like n square times epsilon, where epsilon is very small.
Epsilon is small. Epsilon can be small and still be order 1 in some sense, right? Like 10 to the minus 6 n squared.
I thought you wanted epsilon
number,
to
right?
go to 0. Literally, it's not true.
If you send epsilon goes to 0, you get the 1/8 BPS vanishing horizon black hole.
Right.
The near EVH black hole has a finite entropy. It's epsilon n squared is the scaling of that entropy.
So, sorry, maybe I should ask the question this way. Is the claim that the 116th BPS, 116th supersymmetric extremal black hole can be embedded inside an ADS3? Is that the claim?
Yes.
I see.
We're describing, these systems in terms of these EVH black holes, which have this ADS3 near horizon. And
okay, I'll shut up after very soon. But it's very confusing. Just one more question. So, yeah. Can I describe the whole thing without reference to EVH and just say that if I just don't want to use those words, can I just say that the 116 BPS black holes of Gutovsky and Real, which have ADS5 asymptotics, there is in fact sort of some near or intermediate horizon limit where it's embedded inside an ADS3. Is that the point?
I think you can say that, yes.
I see. That's very interesting. That's surprising to me, but interesting. Okay, we can talk later. Yeah.
Okay. Okay, so we can write down.
Before you go, let me also ask, your parameter epsilon, when you take it to 0, it disappears from the expressions. So the entropy that you reach is the entropy of Gutovsky-Real black holes. No?
When epsilon goes to 0 strictly, you have 0 horizon.
In the scaling. So you have to take some scaling essentially, no?
Yeah.
I'm not talking about the point epsilon equal to 0. I'm talking about this scaling that you are doing in addition to
yes, that's right.
solution.
Yes. If you take epsilon n squared, finite, this is Gutovsky-Real. Yeah.
Exactly. I see.
Okay. Where was I? Right. So we can write down the entropy, and we can evaluate the saddle point. And we generically find some complex entropy, and demanding the imaginary part of the entropy equals 0 presents us with new constraints for the charges. In the EVH limit, we set Q3, in the exact EVH limit, we set Q3 and JB to 0. Black hole's 1/8 BPS, the entropy vanishes, and this is the index. This is a so-called McDonald index with certain parameters scaling this way. The leading term of the partition function scales like n squared, and we can do a saddle point evaluation of this entropy, and this gives 0 and gives the same chemical potentials that we saw in the gravity side. Okay, the near EVH limit, we set things to scale in a particular way, and we find the degeneracy is given by this expression here. In this expression, we have JA and and Q3. So we've got different scalings of various things. So we can do a saddle point evaluation of delta and omega A because they're manifestly large in the story. When we do this, we get this integral with we haven't done the integral over omega B yet, but we have saddle point values for delta and omega, which we designate with these hats. So the trick then is to figure out how to do this this integral with the omega B. So the saddle point evaluation there requires epsilon n squared being large, or alternatively, the rotation parameter A approaching 1, so a very fast rotating black hole. Either choice here, when we do the integral with those considerations, gives us an entropy which scales like this guy here, which is the same expression we saw previously in gravity. So this is the 1/16th BPS solution in this expansion.
But epsilon is still in this expression, no?
Epsilon is still appearing in expression, yes.
So if I want to write, for instance, the charges in terms of A, and epsilon, do you have a feeling how this is? I mean,
yeah, I mean, we can write down, these charges in terms of these quantities. It's in our paper. I don't have it in my talk, but it's in the paper.
okay. But is epsilon just a simple rescaling of n in your case, or is something more? Is it really? Can you reabsorb epsilon in a rescaling of n?
Epsilon's a
Not just in
rescaling
entropy,
that occurs when you scale the coordinates in order to take the near horizon limit.
Okay, my question is the following. If you simply change n by n divided by square root of epsilon, does epsilon disappear from all your equations, not just from entropy, from everything, from the charges, everything, or not?
No, I don't think so.
So it is not the simple rescaling of n.
No.
I see. Okay. Thanks.
Right. So quickly speaking, the CARDY formula is the saddle point evaluation, the universal Laplace transform, and it's related to degeneracy. In the near extremal vanishing horizon limit, the central charge here looks like this expression here, in L0 minus C over 24 looks like this expression there. We can write the degeneracy equation that we saw previously in this form and identify the central charge in L0 minus C over 24. And when we compare to the CARDY formula, we see that the inverse temperature beta will scale like this parameter root 2 epsilon omega b. There's a root 2 mismatch between the gravity and the CFT sort of computation. This root 2 arises from the relation between time coordinates of ADS3 and the ADS5. This root 2 is still a bit mysterious to us. It could be like the famous factor of 3/4 in renormalizing thermal free energy as you go from weak Toff coupling and strong Toff coupling in the usual ADS CFT story. So this root 2 could very well be some strong coupling effect to which a weak coupling analysis is insensitive. Okay, so we can see what happens with this conical deficit angle I talked about associated to this CFT in the infrared, and the analysis there effectively rescales the central charge in L0 by C over 24 by this factor epsilon. I think I got a bit carried away with my tildes. Tilde 24 is also 24. We think about this in terms of a fractionated spectrum, especially in the extremal vanishing horizon case. So the idea being that if we have strings of size r, if they form a long string, the length is nr, the energy gap goes from 1 over r to 1 over nr. So there are a lot of low-lying states in the spectrum. And the description, the physics may be in terms of these low energy states. The operator dual to the story was proposed by Berkhuizen and collaborators. Essentially, you take certain combinations of the fermions that we saw previously, and we can show that these operators satisfy this condition for the EVH black hole. This gives maybe some explicit description of the CFT2 associated to the EVH story. The story in the near EVH case is a bit more complicated, and I don't think we've got a full understanding of that yet. So we can apply a similar tale in higher dimensions. So in ADS4, there is an EVH limit, but the BPS story here has a naked singularity. In ADS6, it turns out that the entropy scale is like t squared. So in the EVH limit, there's an ADS4 near horizon. ADS7, with equal charges, the entropy scale is like t cubed. So there's an ADS5 near horizon. And we discuss aspects of these other EVH stories in our paper. So as a summary, we noticed the techniques for analyzing 1/16 BPS black holes in ADS5 extend to studying these EVH CFT2 solutions. The entropy calculation we've done for EVH and near EVH in the fast rotating limit. We see that the genre transform of the superconformal index, which gives a black hole entropy, is equivalent to a derivation of the CARDY formula. And we show how certain aspects of the IR CFT are realized in the UV CFT, and there's hints of a similar story in higher dimensions. So there are lots of open questions in this game that we would like to understand further. So we'd like a more precise statement of the origins of infinite dimensional conformal symmetries and subsectors of n equals 4 superang moles. In particular, given the details of the ultraviolet CFT, I'd like to understand how aspects of the infrared CFT are realized in full detail. How do we write, for example, the Verozoro generators in the IR based on quantities purely in the UV? We'd like to push the story beyond just matching entropy and understanding what's happening at some microcanonical level, which sends states to states. And one framework that may be better suited for this would be just looking at short multiplets and seeing how short multiplets will flow to short multiplets in analyzing the microscopic descriptions of these geometries. We don't really fully understand this fractionation mechanism from the 4D CFT perspective, and we'd like to see what this means, especially in the near EVH case. As well, in various geometries where smaller ADS factors arise in the near horizon geometry, the smaller ADS factor is really a combination of coordinates on both ADS5 and S5. This, for example, happens in the superstar case. So in the generic setting, where this ADSD is not directly embedded in ADS5, where there's mixing of various things happening, it'd be good to understand aspects of the story, understanding how these more complicated ADS3s arise. We've also recently been thinking about the connection between CARDY and CARDY Verlinda in the story, and we would like to explore this further. So there's quite a bit of work to be done, and I think we've made some interesting progress based on recent developments in this area, and we're pushing these ideas further. So thank you very much.
Thank you, Krishna. All right, questions, comments?
Okay, perhaps I can. So this, well, I guess it's one of the, I remember it's one of the questions that you posted, no? But do you, I guess, well, okay, let me, if I'm asking too much, just please do not say. So do you have a clue of what, this epsilon, you should have some way of seeing it from field theory. I mean, you claim that the same index is the one that governs the entropy of these solutions. No? So in principle, the epsilon should be mappable to a sort of parameter in there. Do you have an idea, or is still very far? You're still far still from that.
So you're asking for an interpretation of epsilon purely in field theory terms.
Yeah, just an unintuitive thing. I mean, the epsilon, essentially you're saying that the same observable, I mean, the index is the one that counts the growth, let's say. No? So epsilon has to be something, I mean, you have to put it in terms of parameters in there somehow. No? Do you have, just from there, one should be able to see something, I don't know, perhaps not, but do you have an intuition, a feeling of what is this thing? Or?
It's a very good question. I really don't, is the honest answer. The way that epsilon was introduced in the story was as a scaling limit on the gravity side. I don't really understand a purely field theoretic description of this parameter. But yes, I agree that it's sort of crucial to understand the meaning of this in field theory in order to determine the origin of these subsectors where there's some CFT with enhanced algebras. Yeah, it's a very good question. I don't have a good answer for you there.
No, thanks very much for the answer.
So can I also bother you a little more on, if it's taking too much time, we can take it offline. I think it's the same thing I'm not able to understand. So were you in my talk when there was this diagram where there's a supersymmetric locus and an extremal locus?
I was there, but please remind me anyway.
Yeah, so I mean, so you have this Gutovsky-Real solution, and
yeah.
there are many deformations of that, infinitely many deformations of that. And in particular, there's one family of deformations which keeps supersymmetry, but you go away from extremality. These are sort of bad solutions in the Lorentzian theory. They have CTCs, but in the Euclidean theory, there's some sort of real slice which makes it into some cigar type of geometry. Then there's another one where you break supersymmetry, but you preserve extremality, and and then there's some arbitrary linear combination allowed. Now, I'm just trying to understand where in this moduli space do your solutions sit? Which solutions are you considering? You're also deforming away from the original black hole solution, if I'm correct?
We're deforming away. You're asking about the near EVH solutions. You're asking which solutions are these?
That's right. So the one you're trying to describe using some CARDY formula, that's the one I'm interested in.
So we can think about these as deformations away from the 8th BPS.
But in fact, they're 1/16 BPS. Is that what you said?
They're 1/16 BPS. Yeah.
So they are supersymmetric solutions then?
Yes.
So then in my diagram, they should fall on this supersymmetric locus. But are these good Lorentzian solutions?
I believe so.
That's
no.
But
I mean, if they are on the line, they are not. They should not be.
Yeah, if they're not literally I mean, our result was that if you impose supersymmetry, then there's only one point. It's not our result actually. This goes back to all the papers you were quoting. If you impose supersymmetry, then there's only one point, which is literally the one considered by Gutovsky and Real, which has sensible Lorentzian interpretation.
Exactly. Mm-hmm.
Maybe my collaborators can chime in. I don't think there's any issue here with Lorentzian.
I mean, the issue. But this is in these papers of.
Svetic.
Yeah, exactly. Thank you. Yeah, CC. Yeah, exactly. Svetic and yeah.
I'll have a look. And let me get back to you offline. Maybe I don't have any. I don't think these are pathological in any sense, but I don't. I'll have a look.
Okay. All right. Yeah. Maybe we can continue this discussion. I mean, there's some thing to be understood, I think. But okay, we can talk later offline.
Okay, so if there are no more questions, let's thank Vishnu again. All right, that's it for the morning session, and we'll reconvene for the last talk of this workshop by Atish at 2 o'clock Lisbon time.
All right.
Thank you.
Thank you.
Nice session.
Vishnu, send me the slides, okay? Don't forget.
Will do.
All right, thanks. I'll see you later.